Hello, everyone. Hello, good afternoon. My name is Eli White, and I'm a software engineer on the React Native core team at Facebook. Along with Pasquale and Tom, who you're going to hear from a little bit later, we're part of a group that's responsible for developing a lot of the tools and technologies that we use to develop our mobile apps at Facebook. Many of these tools are open sourced and widely used, and today you're going to hear updates on 3 of these technologies: React Native, ComponentKit, and Litho. In a bit, Pasquale and Tom are going to come up, and they're going to talk about how ComponentKit and Litho have evolved to enable some of the most important and highly optimized features in our apps. But first, I want to share a bit about what we've been working on in React Native over the last year, and some of what to expect in the future. The teams in our group focus our work specifically on the needs of the product teams that use them. React Native is used by many of the products in the Facebook family of apps, from Ads Manager to the Oculus companion app, as well as many of the features in the Facebook app as well, from Profile About, Dating, Safety Check, and many more. But for the last year, we've focused almost exclusively on Marketplace, our largest consumer. Marketplace is one of the newer tabs in the Facebook app, and they use React Native for almost every part of the product. In the short amount of time that Marketplace has been around, it has grown to be used by 1 in 3 people in the United States. I want to spend some time today to share a bit about Marketplace's journey building with React Native and some of the lessons that we've learned along the road. From the beginning, Marketplace has happily been using React Native, and there are 3 reasons that are most important. First is the size of the React ecosystem. The React ecosystem is massive. We don't really know exactly how many React engineers there are in the world, but we at least know the lower bound. There are 1.6 million people who have the React dev tools installed in Chrome. 1.6 million people. This massive pool of talent has enabled Marketplace to hire and train people to be productive on mobile very quickly. Marketplace has also enjoyed the fast iteration speed. When you change native code, you have to make your change, compile the app, reinstall it, and then navigate back to the screen that you were working on. With React Native, you can change your JavaScript code and see those changes instantly. This iteration speed was really important for Marketplace early on because it helped them find product-market fit. And it's since become invaluable as they experiment and build new features. The third reason it's been really valuable for Marketplace is their ability to share code. Now, this wasn't an initial goal for Marketplace, but they found that they've been able to share almost all of their product code across Android and iOS. This means that they're able to build their experiences faster with a smaller team. But even though Marketplace has been really successful, it hasn't always been smooth sailing. In 2018, there were major concerns about the product and the experience of Marketplace. Marketplace ran some user studies, and they found that people were confused and frustrated with the product. People struggle to find and contact sellers, which is one of the key metrics for Marketplace. And the performance of Marketplace was really bad as well, especially on older Android devices. This feedback led us to question the viability of React Native. We weren't sure whether it was even possible to build experiences with React Native that could meet our bar for quality and performance. If we were going to continue investing in React Native, we had to prove to ourselves that we could meet this bar, that we could build these experiences. So we spent the next year working with Marketplace to focus on understanding the product experience and how we can improve it. I want to share a bit about what we've learned, starting with how we improved quality. Up to this point, quality wasn't a priority for Marketplace. The focus was product-market fit. But at this point, Marketplace clearly has product-market fit, and they wanted to focus a bit more on the experience and consistency with the rest of the app. At the time, Marketplace was using colors that weren't found anywhere else in the app and had inconsistent spacing between and around elements. It also had navigation patterns that were unique to Marketplace and weren't shared with the rest of the app. Now, none of these problems are inherent to React Native. We know that the community has built beautiful apps using React Native. We know that it's possible. But internally, we needed to improve the reputation of React Native by improving the polish of the flagship product that's built with it. The iteration speed on native is really slow, which means that one of the side effects of that is that it's often faster to find and repurpose code from somewhere else in the app rather than building what you need for yourself now. Marketplace found that the opposite is true with React Native. It's often faster for them to build exactly what they need when they need it, rather than finding and repurposing something else in the app. Now, this is great for Marketplace because it means that they're able to get that product market fit. They're able to iterate really quickly. The problem is that it can lead to some inconsistencies with the rest of the app because you're not sharing the same code. So one of the things that we did to improve this is we worked with Marketplace to build a high-quality component library that's consistent with the design and aesthetic of the rest of the Facebook app. This component library was quickly adopted by Marketplace and many of the other product teams using React Native at Facebook. This enabled consistent, polished experiences by default. Once Marketplace started using this, it started looking like the rest of the app, but there were still some interactions that didn't feel great. Marketplace wanted to use a bottom sheet in the product. And again, they found that it was quicker to build what they needed, the bottom sheet experience that they wanted, in JavaScript as fast as they could. The problem is that we had a bottom sheet in native that's used everywhere else in the app. And this native bottom sheet is really well polished. It works on all the devices we want, and it looks and feels great. Because Marketplace was building so fast, they weren't able to prioritize getting their implementation to match this native experience. And people noticed. The bottom sheet didn't feel like they expected from everywhere else in the Facebook app. So to improve this, we worked with a native engineer to expose the native bottom sheet that we use everywhere else in Facebook to React Native. This enabled every React Native screen in the app to be consistent with everything built with other technologies. Now, it's important to note that the container of this bottom sheet is native. The snap points, the animations, the handle, that's all rendered in native. But the contents of the bottom sheet, that's all React Native and rendered by the product. This is one of the core advantages of React Native. You're able to utilize native controls, whether they're provided by React Native or by the framework or by you in native. At this point, Marketplace was consistent. But consistency with the rest of the app is table stakes. We had to raise the bar for quality. So we challenged the designers working on Marketplace to add the touches of delight that they've always wanted to see in the product. There are a couple of experiences that the Marketplace designers had always wanted, but they thought they weren't possible to build them in React Native. Once the designers and engineers started looking at building these experiences, they found that they weren't just possible in React Native, but that React Native made it easier for them to build them. One of these experiences, one of the things that Marketplace has always wanted, is a more seamless transition from the feed to the items details page. The previous transition was the standard push navigation transition, where the next screen would come on top of the current one. The designers wanted a shared element transition, and this is something that we've wanted in the Facebook app for a really long time, and it's been really hard to pull off. Marketplace was one of the first experiences in the Facebook app to bring this experience to life. They found that the animations in React Native helped make this experience possible. The second touch of delight is when you find an item and want to message the seller. The way it worked originally is you would touch a button and be brought to a messenger flow where you could have a conversation with the seller. This was fine, but it was confusing, and people often would be pulled out of their flow and would not return to Marketplace to keep looking at more items. So one of the things that the designers wanted is an inline composer, a way to talk to the seller from without leaving the details page. So they built this experience. And just every time I see this video, I'm just like amazed at how well polished this looks, and the animations are great. I'm really excited as we bring more kind of things like this to the Facebook app, and that Marketplace is leading the way. At this point, Marketplace is one of the most polished experiences in the Facebook app. Marketplace ran some user studies and found that people's perceptions had improved, and this was reflected in the key metrics of the product. This work with Marketplace taught us 3 lessons that we've been bringing to the React Native community at Facebook, and I want to share them with all of you. The first is that when you're building with the platform, it's important to have people on your team who know the platform. React Native has enabled web engineers to come and have an impact on mobile. But the difference is that the quality bar on mobile is way higher than the quality bar is on web. It's important to have people on your team who know the expectations of the platform and know what you can build with and what already exists. The second is that well-polished experiences aren't free. You have to prioritize this work. It's important to your users that your app looks and feels good and is consistent with their expectations and everything else in the app. If you have animations that are missing frames or have visual jank, people will notice. If you're part of an organization that frequently pushes back on design, saying, this isn't possible with React Native, maybe take another look. If you need some inspiration, there's a bunch of videos online that take complex experiences built in other apps and show how to build them with React Native. The third lesson is that building with React Native does not mean you can only use JavaScript. Native engineers are highly valued and leveraged in a React Native ecosystem. They have the skills and the expertise to expose native components and behaviors for everyone working in JavaScript to be able to use. Once these lessons were ingrained in us at Facebook, Marketplace had a new confidence that they could build all of the quality experiences that they wanted. And this confidence enabled us to shift our attention a little bit from quality to performance, specifically the time needed to navigate and render Marketplace feed. When we started this work, we knew what people meant by fast. We knew what their expectations were. But when we started measuring Marketplace startup, we found that we were way off from those expectations. At best, this experience was frustrating. And at worst, it meant that users were giving up and not waiting for Marketplace to load. So we partnered with Marketplace to break down this chunk of time and to see where we can make improvements. We then looked into each big chunk of time, starting with React Native startup. The React Native framework is loaded once when it's first needed. And Marketplace is the largest product in the Facebook app that uses React Native, which means that the framework is often not yet initialized when people navigate to the surface. We found that we were spending a ton of time doing disk I/O, especially on mid-end Android devices that have exceptionally slower disks. Of this startup time, more than half of it was spent initializing classes that are needed to expose native functionality to JavaScript. We call these classes native modules, and we were loading 188 native modules during Marketplace startup. Now, it's really common for teams using React Native to need to expose this native functionality to JavaScript. This is part of React Native. But we found that we were loading every module for every team using React Native for Marketplace startup. But for Marketplace Home, the only thing we actually needed to load were 7 of these modules. So we changed our infrastructure to lazily load these native modules, significantly reducing React Native startup. Now, we made this change with a bunch of internal infrastructure, but our team is working on a rewrite of the entire native module initialization system to bake in these lessons by default. And this is going to be coming to all of you sometime this year. The next thing we looked at is the JavaScript and render time. This is your regular product code that you're building in React Native, your typical JavaScript product code. A significant chunk of this time was just spent loading the JavaScript bundle. Similar to native modules, we found we were doing a whole bunch of unnecessary work. When loading a bundle, you must first load and execute every module that is transitively required. And all of this has to finish before any of your product code can run. For Marketplace in the Facebook app, this meant that we were loading and initializing every app product using React Native in the Facebook app, all of their JavaScript code before we're able to start doing any of the work to render Marketplace Home. So we made an optimization to only load what's necessary. And so for Marketplace Feed, this means only loading the code for Marketplace Feed. This optimization is called inline requires, and this has improved our JavaScript time and will continue to keep Marketplace fast as more products continue to use React Native. This optimization shipped to open source in March, and it's off by default for now, but we want to get feedback from all of you on how it's improved the performance of your app so that we can turn it on by default in the future. If you wanted to turn it to true, change inline requires to true in your Metro config. The next remaining biggest chunk of time was the network and server time. The way Marketplace was making the network request is they were waiting for React Native startup to occur, for the VM to initialize and load your JavaScript, for product code to run, and then for the product code to make the network request. Now, this is a long time to wait. We made an optimization to make this network request from native instead, so we can do this in parallel with all of our other work. Making a network request happen as early as possible has become one of our key strategies, regardless of what technology the product is built with at Facebook. The Marketplace team also made a bunch of optimizations to their JavaScript and render time using the React Dev tools. And using similar profiling tools on the server, made a bunch of optimizations there as well. This work led to drastic improvements in people's perception of Marketplace, and it was reflected in the key metrics of Marketplace. At this point, React Native was no longer a concern for Marketplace. They felt like they could build anything they wanted without the framework holding them back. This confidence enabled us to invest in bigger bets for React Native. And one of those bigger bets is an opportunity to rethink the foundations of React Native. The foundations of React Native that exist today are the same as the ones that were open sourced 4 years ago. Our team is working on a rewrite of the core with shared cross-platform C++ to unlock a couple of specific things. The first is improved interop with native. One example of improved interop is being able to embed React Native views into screens that are built with other technologies. For us at Facebook, this means ComponentKit and Litho. Second, we're changing the way that JavaScript communicates with native. And this will give us a new ceiling for performance. And third, this work will unlock some really exciting new capabilities from React, such as improved cooperative scheduling. Now, it's important to note that all of these changes are backwards compatible. We have thousands of components at Facebook that use React Native. We can't just break them. We have to make sure that they keep working as we make these improvements. If you want to learn more about the architectural improvements that we've been making, check out our talk from ReactConf last year, where we went into a bunch of additional detail. As we've been making these architectural improvements and getting confidence that it can power the experiences that we need, we've been able to start shifting our attention a little bit to the community, specifically how we can bring all of these improvements to all of you. The React Native ecosystem is growing rapidly. And the projects and plugins that people rely on are better maintained and are supporting more of the features that people want. We're seeing the same improvements happen to the core of React Native. There's been an immense number of commits from Facebook and community contributions. In the first 4 months of the year, we've had over 900 commits to the framework. Now you might ask, is this too much change? Is this stable enough for us to base our framework and our company's product on? Well, one of the key benefits of React Native is that Facebook runs React Native from master. This means that we validate every commit in production across the billions of people using the Facebook app around the world. By the time we ship a release of React Native, this code has been running in production for about a month. We have high confidence that it will work on all sorts of device types and network conditions. Because of this velocity of change and the architectural improvements that we've been making, we started a new repository called Discussions and Proposals, and we've been using this to share our plans and to hear feedback from all of you on the big changes that we've been making. Now, this level of transparency is really important because for the last 2 years, React Native has had the second highest number of unique contributors across all of GitHub. In 2018 alone, we had over 10,000 people contribute to the framework. Now, with all of these contributions, it can be really hard for us to keep up with the amount of pull requests that we get every day. So we've been working on improving our infrastructure to be able to more timely review and merge these pull requests. And a fun side effect of this is that the community has noticed and started sending us even more pull requests. We went from receiving 3 PRs a day to receiving 8 PRs a day, and merged over 600 PRs from the community in the last couple of months. React Native has improved a lot over the last year. We have confidence that we can build the quality and performant apps that we need. And we're investing in architecture that looks at how we can bring React Native into the future. But as we look to the future, we're also revisiting some of the assumptions of the past. React Native was created with the tagline, "Learn once, write anywhere." But as we've seen, Marketplace is already sharing almost all of their product code across Android and iOS. Now, these are the platforms that we maintain, but there are many companies that support others. One of the things that we've heard from many companies using React Native is they wish they could share the same code across mobile and web. Expo is a company that provides a tool chain for building and deploying high-quality React Native apps on iOS and Android. They recently added support to use the same code base to render to web as well. And one of the other biggest platforms in the world is Windows. Microsoft maintains React Native Windows, which enables engineers to use the same knowledge and code base to render to their platform as well. And Oculus uses React Native for some of their VR apps. This is Oculus Venues, a large-scale social experience in VR written with React Native. React Native has helped many companies around the world by enabling engineers to move faster and build for multiple platforms. But at Facebook, it's only one of the technologies that we use to build our mobile apps. To talk about two of our others, ComponentKit and Litho, I'd like to welcome up Tom.
Thanks, Eli. So 5 years ago, we introduced ComponentKit, and 2 years ago, Litho. And these are native UI frameworks that we built specifically to power newsfeed on iOS and Android. At the time, we were looking to build the best possible technology to power our feed rendering. And for this reason, the design of these frameworks was oriented towards being able to move work off the main thread so that we could ensure we could achieve smooth scrolling, even when rendering very complex UI. And to achieve the goals for newsfeed, we went with the same concept that React has, building a declarative way to define UIs. And this is really successful in newsfeed, but really know that. Today, we're going to talk about how we've evolved these frameworks over the last few years. During this time, the use of these two frameworks has expanded way beyond just newsfeed and Facebook. And we're now rendering most of the critical interactions in our applications with these technologies. In fact, most of the time that you spend looking at Facebook and Messenger is time spent looking at surfaces built with ComponentKit and Litho. And examples of surfaces that have adopted these frameworks are Composer, Watch, Groups, Stories, and Messenger. So we said that we built these frameworks for newsfeed. Why have we started using them in other surfaces? Well, the benefits of building UI using Facebook's reactive programming model applies to all surfaces and not just newsfeed. And just like with React, we've learned that building UI using components scales extremely well when you have a code base with thousands of commits a day. So ComponentKit and Litho are how we build most of the UI in our apps. And the declarative nature of ComponentKit and Litho means that engineers tell the framework what they want to do and less of how to do it, leaving it up to the framework to determine more of the how. And as product foundation, this is super important to us because it means that framework-level optimizations that we build, when applied, are amplified across our code base and across our apps. So with this in mind, we've been evolving our frameworks with a focus on rendering speed, developer experience, and expanding capabilities. And today, we'll discuss some of the more interesting solutions that we've come up with. But while some of these were very specific to either iOS or Android, there was one area of capability where we ended up with pretty much the same solution on both platforms. And I'd like to invite Pasquale to come on stage and tell you more about this.
So with Litho and ComponentKit, we introduced an API to declarative describe UI. When we went and integrated this new API in our newsfeed product, we realized that describing the UI of a newsfeed story, for example, was just part of the complexity. Turns out that building a list with such heterogeneous content is also a hard problem in itself. Efficiently rendering a dynamic list in which content can continuously change requires having a very good way of understanding exactly what is changing for every update. Luckily for us, newsfeed already had a lot of logic to handle list operations, so at the time, we could focus just on converting each individual piece of UI. When we started adopting Litho and ComponentKit in other surfaces, though, this wasn't always the case. And we found that we were solving the problem of updating lists efficiently over and over again. That's why we decided it was time to build a new API to do that instead. And we call this API Sections. Sections, as the rest of Litho and ComponentKit, is based on a simple declarative API. It allows to easily flow complex data models into the UI representation, and it's built around composition to easily enable lists composed of heterogeneous pieces of UI. On top of that, Section was built with the usual focus on performance and can automatically calculate the optimal set of operations needed to update a list without blocking the UI thread. So let's look at a simple example. Today, I'll show you Android code, but you can assume that the same concepts apply to iOS as well. This is one of our Litho sample applications, a list of some of the most influential lithography artists. Usually, to implement such lists, you would start from either an Android adapter or an iOS data source. Let's see what this looks like in Sections. So here it is. This is pretty much all you need to write to define the list we just looked at. And if this code looks similar to the samples you might have seen for Litho, it's because the API is fundamentally the same. Instead of defining a component, in this case, we are defining a section called artist section. And the only thing that artist section has to do is to define how the input, the list of artists, is used to populate our list. And it does so by using one of the section API primitive, a datative section. A datative section is something that, given an homogeneous list, a render function, and a diffing function, renders our UI. Now, let's make this slightly more interesting. We did say that one of the advantages of section was composability. So I wanted to show you what this means in practice. Say that we want to add a loading indicator at the bottom of our list, for example, when we are loading more data to fill the list. On both traditional Android and iOS, this would include some tedious work with view types, reuse identifiers, and quite a lot of extra code in your adapter or data source. In our section, all we have to do is to add a new prop, loading, that defines whether we are loading new data or not, and these 4 lines of code. This code, based on whether loading is true or not, will render a single component section with a loading component. And what the single component section is the other major primitive in the section API, and as the name might suggest, is a convenience API to render individual elements in a list. Lastly, I'd like to talk about performance. We mentioned that section enables efficient rendering for lists. In both Android and iOS, lists are pretty smart in terms of what they render when something changes. In this example, when adding the loading spinner, the list will figure out that nothing else changed on screen, and it only needs to compute layout for the loading spinner itself. In practice, though, in real-world applications, calculating the set of changes for a list can be really complex. And we found that a lot of times, we ended up falling back on invoking notify us set changed or reload data, depending on the platform. Doing so is the equivalent of saying, I know that something changed in my list and it needs to be re-rendered, but since I don't know what, please re-render everything. Sections removes the complexity of calculating this change set from the product code and never falls back on the inefficient way of updating your UI. It's for this reason that adopting the combo of section and ComponentKit or Litho gave us huge performance improvements everywhere we did it. Enforcing efficient diffing by default translated in huge performance wins, and we measured up to 50% less frame drops in surfaces that were converted to this new infrastructure. Sections is now the de facto standard for rendering lists in many of our applications, and it's a great example of how we ended up sharing the same concept and finding shared solutions, even when building for entirely different platforms. There were cases in which we instead focused more on individual frameworks, and I'd like to invite Tom back on stage to tell you some of the things that we changed for ComponentKit.
So as the use of ComponentKit has grown, what have we done to ensure that the framework keeps up with the needs of our engineers and our products? Well, one of the areas where we've made investments in is rendering speed. And faster rendering means that the UI redraws with less delay after an update, whether as a result of user interaction or data model changes. So let's have a look how ComponentKit typically works. You see here we have the main thread, and this is concerned with the mount process. And this is the process where views are added or removed or updated. And because this interacts with UIKit, this has to be performed on the main thread. And much of our optimizations have traditionally focused on reducing the number of operations that happen here. And then we have a background thread, and this builds the component tree and performs the physical layout of all of the components. And every time there's an update to the UI, we perform the same process over again. We rebuild the tree, perform layout, and mount the changes. And this rebuild of the tree, or reflow of the UI, is how we achieve the precise UIs that accurately reflect the current state of our data model. And unlike traditional UIKit code, The UI here is not merely a collection of state updates over time, and we know that this is less error-prone. And you'll note here that the tree build itself is an artifact of having a reactive framework. The component tree is our alternative representation of the UI, and it's what allows us to provide the benefits of declarative programming. It's also what allows us to perform layout on a background thread. And these are all great things, but they're not entirely free. And what we've discovered is that component tree creation often dominates over layout time. So why does tree creation dominate over layout? Well, one reason is that component trees can just get super large because the UI can get very complex in terms of the number of individual elements that need to be represented on screen. And another reason why tree creation often dominates is that components contain product code or business logic. And being able to put this logic inside a component is part of what makes reactive code easy to reason about. And it's super cool that ComponentKit's able to execute this code in a background thread so that we can maintain our scroll performance. But nevertheless, we know that a single slow component will slow down creation of the entire component tree, and thus increase the time it takes for UI update to take effect. So in ComponentKit, components are written in Objective-C++. And because of this, they aren't really restricted in what they can do. So here's an example of a component that's slow to create. The component performs an expensive image processing operation, a blur in this case. And we could argue that the product engineer should be more careful, they should cache the image, or blur it asynchronously. But I think you could also argue that asking them to do so would make the code less declarative and certainly require more work for the product engineer. So this is an extreme example of a heavyweight component, but I think in any case, we have to accept that there will always be product code that does non-performant things outside of the framework's control. So as a reminder, the reactive programming model conceptually re-renders the UI with every update. And you recall, this is what makes the code easy to reason about and what gives us the precise and accurate rendering and layout that we want. But let's say that we observe that updates only change the colored components. The rest of the components are unaffected by the updates. So wouldn't it be great if we only had to rebuild parts of the component tree that have changed and reuse from previous generations the parts that haven't changed? And that's what a new render component API enables. So as long as you write components with the new render API, ComponentKit automatically identify parts of the component tree that sit outside the path of an update, and then repurpose or reuse the subtree from the previous generation within the new component tree. And this reuse avoids the cost of unnecessarily recreating those components. For the engineer, they can still reason about the UI as if the component tree is being recreated in full, so the optimization is basically free and transparent to the engineer. So we're able to safely reuse components from previous generations because the components are immutable, meaning they're also thread safe. And components are unidirectional, meaning they can exist across multiple trees from different generations. And depending on the UI and on which component has actually changed, the savings from reuse can be significant. So when we started rolling out render components, we found that for some services, we were able to achieve a 50% improvement in update speeds, meaning a more responsive UI. So I've talked a little bit about performance, but recall I also wanted to talk about developer experience. And one of the things we wanted to do was make writing components with ComponentKit as easy as possible. So basically get more work done with less lines of code. Developers define more of what they want done and less of how it should be done. Here's code for a basic component. The component has an initializer that returns a flex box that contains an image and some text. And you notice here that the initializer doesn't return until its own children and recursively their children and so on have also been initialized. And this eager creation of components proved to be an issue when implementing tree reuse with our render components API. So the original architecture of ComponentKit wasn't built for partial rendering, and it expected that trees would always be built in their entirety. So building just the root component of a tree meant waiting for the entire tree to be built. It was all or nothing. Here's that component again. The solution to the eager creation of component trees was to make the initializer trivial and to move the code that builds the component from the initializer into a separate method that then can be managed by infrastructure. So we call this method the render method. And this is what a component rewritten as a render component looks like. So we have a simpler initializer and the render method, which does the heavy work of building the contents of the component. And to be absolutely clear here is the fact that the render method is separate and may not even be called by infrastructure that gives us the performance boost. If render isn't called for the current generation or for the current UI reflow, then it means that infrastructure is reusing this component's render results from the previous reflow. So render components require developers to write a little bit more code, specifically this code in the initializer. And all this code does is take the component's properties and save them so that they can be used later on by the render method. And so this code is kind of boilerplate code, and we wanted engineers to write less code. So we introduced a new way to define components inspired by Litho. Instead of writing a class with an initializer and a render method, you define a component spec. And a spec is a set of raw functions grouped inside a namespace. In this case, you see we have the same render functions that we had before, but note that we don't actually need the initializer anymore. So how does a component spec turn into a component? Well, we've written a tool based on libclang, which we call CK CodeGen. And as its name implies, it's a code generation tool. It parses and processes the component spec, and then generates all the associated boilerplate code that turns the spec into a fully fledged component. So in the case of the simple component that we had before, it would generate a CK component class with an appropriate initializer and a render method that delegates to the render function that was defined in the spec. So by using component specs and code generation, ComponentKit becomes more declarative, and this gives us wins. So components are more concise to define. Developers can't accidentally introduce state because by adding ivars to a class because there's no class for them to add those ivars to. Other component features, such as event handling or issuing state updates, also have associated boilerplate code, which we can now also generate using code generation. And because infrastructure manages more of the code, future optimizations that we implement can be realized without needing to change the code of existing components. Here's one such example of an optimization that we've already been able to introduce. So we observed that almost 1/3 of our components are pure functional components. That is, that they are only a composition of other components and without additional functionality such as state or event handling. And so these components can remain as functions, and they don't need a unique class or type. So one of the optimizations that we've built is simply for CK CodeGen to not generate a class for these type of components and let them remain as pure raw functions. So Objective-C++ is our dynamic language, and each class comes with a lot of metadata. Every component that doesn't require its own class saves us over 200 bytes in the resulting app binary. And given that we use ComponentKit almost everywhere, by removing unnecessary classes or types, we end up with meaningful space savings. And this translates to not only a smaller size on the App Store, but because we avoid also having to load this metadata on startup, we get faster app launch times as well. So I hope you've gained an insight into how we're continuing to invest in ComponentKit to improve the developer experience and to improve the performance of our apps. And now I'd like to ask Pasquale to come back on stage and talk through some of the investments we've been making in Litho.
So you have already heard during this presentation how important it is for us to be able to render a new screen as quickly as possible. So that's exactly where we focused our performance effort for Litho in the last couple of years. One of the fundamental principles we built Litho around was actually performance. And when we were designing the framework, we wanted to make sure we could render smooth UI at all times, especially when scrolling, and we succeeded at that. On the other hand, in the initial design of the framework, we didn't put as much emphasis on rendering a new screen as quickly as possible. Once we decided that was going to be our focus, we started thinking about how the fundamental performance properties of our framework could be applied to this problem. We already know that we can move part of rendering to a background thread, and that's of course great when you can do the computation ahead of time. When you look at what happens when you render a screen for the first time, though, there is not really a lot of time you can use before the rendering itself. You usually have a number of UI elements that you want to draw, and for each one of those, you have to run layout and then draw. And this traditionally happens sequentially. So is our threading model not useful for first rendering? Turns out likely this is not the case at all. With Litho, we are naturally splitting rendering into two independent steps, and this means that there is an opportunity to use parallelism to make things faster. The first thing that we tried was to simply schedule the layout computations on a background thread whenever we needed to render a new screen. And our threading model at the time was pretty simple. The idea was that if the UI thread needed a layout, before the background thread actually computed it, we would just go ahead and calculate one on the UI thread in line. As you can see from this graph, this is not a great solution. The UI thread almost always ends up having to recalculate a layout that was already happening on a background thread. And while by chance, the UI thread could from time to time find a layout ready, like in case of layout number 3 here, it's easy to notice how very often the UI thread ends up recalculating layouts even if they're almost ready. So to address this, we changed our threading model quite fundamentally, helped by some contributions from our open source community. We now have a way to determine that the layout for a given piece of UI is happening on a background thread and wait for it to complete instead of recomputing it from scratch. When this happens, we also momentarily bump the priority of the thread that is calculating that layout to ensure that it runs as fast as possible. This was a major improvement in our initial rendering performance, and we can now exploit the fact that most devices out there come with multiple cores. While good, this solution was still not ideal though. As you can see, the UI thread is often blocking on a lower priority thread, and we lose parallelism every time this happens. So can we do better than that? I earlier said that the first thing that we do when we render a new screen is to lay out and draw all the pieces of the UI for that screen. But turns out that that's not 100% correct. Before a new screen starts rendering, there is usually some time spent initializing the activity or fragment and doing things like dependency injection. That means that we can actually take advantage of that time if we already know what we're going to render. And that's exactly what we ended up doing in a lot of our most critical interactions. And when we managed to apply all these optimizations, we now only spend time on the UI thread to actually draw things. So to recap, our threading model was built with the idea of decoupling drawing and layout calculations, and this fundamental characteristic make it possible for the framework to really take advantage of the parallelism modern devices can express. So this is a good part of what we focused on in terms of performance, but of course we also worked on making Litho a more powerful and mature framework in itself. And as we adopted the framework in more places, we realized that we really needed to improve our support to dynamic UIs and animations. That's why one of our major efforts in the last couple of years has been to introduce a new API for layout transitions. We wanted to create a simple yet powerful way to describe how layout changes should be animated between screens. And we call this new API transitions. The main principles behind transitions are animations are defined with a simple declarative API. All animations should be interruptible and reversible so that we never end up with straight jumps for any pieces of UI. And all animations are by default physics-based to offer a more realistic animation effect. Let's have a quick look at how this actually works. This is a very simple first example, and we want to simply animate the X property of the square every time it changes in a new layout. All we have to do is write these 2 lines of code. We target the square, and we'll say that we want to animate the X position. Pretty simple, right? For more complex cases, you actually might want to specify a choreography for your animation, defining ordering between different pieces of the animation. Transitions offers API to do that out of the box. And in this case, we're animating the Y position for each one of these boxes, and we're just delaying the beginning of each animation by 300 milliseconds. We mentioned that we wanted our animation to be interruptible by default, and what that means is pretty easy to show here. Oh, I'm sorry. I think this was supposed to play video. Anyway, what we can do is simply realize when an animation needs to be interrupted, and we simply can bring them back from the position they were in. We wanted this animation to be also as convenient to write as possible, and that's why we also provide a way to simply tell the framework that anything that might be changing has to be animated automatically. To achieve this complex animation, for example, all I had to do was to ask the framework to detect what was changing on screen and animate it for me. And again, the video doesn't work. It's all right. And finally, we can bring this all together by mixing choreography and automatic transitions. In this case, that finally works. For example, we want everything to animate automatically, but we want to specify, for example, a different animation for text. And that is exactly what we're doing. The transition API has already been used to implement hundreds of transitions. One of our most dynamic products, Stories, has most of its animations built with this technology. So to recap, today we covered how we've been evolving 3 of our main technology we use at Facebook to develop mobile apps: React Native, ComponentKit, and Litho. We use different technologies because we have teams with different needs and diverse technical background. We still aim to ship great product, no matter which of these technologies gets used. CK, Litho, and React Native are currently being used by hundreds of engineers at Facebook to build products that reach hundreds of millions of users. And they're all constantly improving to provide better quality, performance, and capabilities. If you want to come talk to us and hear more about any of these technologies, we'll be at the open source booth in room 220A, so we'll see you there. Thank you.